Today we're going to talk about the potassium-argon isochron dating method. Potassium has three naturally occurring isotopes. Potassium-39 and potassium-41 are stable. Potassium-39 makes up the bulk of the isotopes at 93%. And potassium-40, which we'll be looking at for this dating, is radioactive. It's not stable, and it's about 0.01%. The half-life on potassium-40 is 1.2 times 10 to the 9th years. It's primordial, which means its half-life is longer than the age of the Earth, so it can be used to date things that are older than the Earth, like meteorites. Potassium is a soft silver metal. Potassium is used as fertilizers, mostly potassium salts. Potassium hydroxide is used to make detergents, and potassium is, of course, essential in biological functions. The ions help cells and nerves to function and muscles to contract. We will be looking at the decay of potassium-40 in our potassium-argon dating. This dating is from the information of the decay of potassium to argon-40. And this comes from electron capture, positron emission, and electron capture. In the next few slides, we'll simplify this decay scheme. But what we are looking at in our dating is the decay of potassium-40 to argon-40. We will not be concerned with the decay into calcium. However, it does decay into calcium as well. Argon has three stable isotopes, the largest percentage being argon-40 at 99.6%. And almost all of the argon-40 on Earth is radiogenic, and radiogenic means it's produced from the decay of something else, and argon-40 is produced from the decay of potassium-40. Something else that's important to our dating is atmospheric argon has a constant ratio of argon-40 to argon-36 at 295.5, and we'll talk about that later. Argon is an inert gas, and it's used when inert environments are needed, so it can stop reactions, things that would oxidize with the oxygen from the air, from happening by blanketing things in argon gas. So it protects welding surfaces and other reactive surfaces from oxidation. And it's also used in fluorescent tubes and light bulbs. And I thought this picture was kind of interesting. So here is a light bulb, and argon gas is excited, and it does not give off the light when it goes back down to ground state. It gives off ultraviolet light, and that ultraviolet light hits the fluorescent coating on the tubes in this light bulb, and that produces the visible light. Isochron dating is a technique that we will be using to date our samples. It's a process that uses radiometric isotopes. This is an isotope from a decay of an element for dating. And down below on the right, I have our decay scheme. And potassium, like we said, decays into argon and calcium, but for our purposes, we will just be concerned with the decay of potassium-40 into argon-40. So for our potassium-argon dating, potassium crystallization during a volcanic event will be dated through this decay of potassium-40 to argon-40. And when we take these samples, the measurement of potassium-40 and argon-40 in the sample will be measured to create an isochron graph. So iso meaning equal, chron meaning time. So we have something equal to time. And with our measurements, we'll be creating a graph where the slope will be equal to the time of crystallization. When we take these samples, we are making a few assumptions. The system or the sample will be enclosed, so no radiometric argon has escaped. And the samples will also be cogenetic. That means they come from the same system, that was created at the same time. All samples will have a homogeneous distribution of potassium-40 and argon-40. So when we take our measurements from different samples that are all cogenetic, they will have the same distribution. We're also going to assume that the atmosphere has contaminated our sample, and in the atmosphere there's argon-40 and argon-36. Argon-40 will be subtracted from the decayed argon-40, so we can get the argon-40 that's just from the decay. And we'll be talking more about all of this. The samples we use to date are taken from a level of the Earth that has to do with a volcanic eruption. So here's how it works. We have a magma chamber, and the potassium goes into our samples in that magma chamber. So does some argon, but because argon's inert, it won't react with anything in the magma, and because of the high temperature and the fact that argon's a noble gas, it will escape. So at this point in that chamber, our samples will contain potassium but no argon, and the clock will start when that volcano erupts. So the volcano will erupt, and when it does that, our samples will only contain potassium, so everything after that will have argon due to the decay of potassium only, not from the introduction from inside the magma chamber. Now, when it erupts, it will also be contaminated with some argon-40 and argon-36 from the air, and we'll use these ratios in our mathematical formulas to subtract that, so we're looking just at the argon formed from the decay. So on the right is a picture of a takeout of the Earth. So we're digging down, and what we see here is a fossil layer, and we're going to assume that's what we want to date, and that happens between two layers of a volcanic eruption. So this date has to be between the dates of either volcanic eruption. So we're going to date both levels. And remember, we have those assumptions that the volcanic rock or minerals or samples that we're taking has enclosed the argon gas. So the argon gas from the decay of potassium-40 cannot escape. It's in a closed system. Okay, when the eruption happens, the atmospheric argon will contaminate the sample and must be subtracted. So our atmosphere contains argon-40 and argon-36, and this ratio is constant. And so our sample will contain argon from the decay and argon from the contamination, and so the contamination must be subtracted from the total argon to get just the argon from the decay. We just saw a picture that showed levels of Earth, and our fossil was sandwiched between two different layers of volcanic ash. One layer is considered the same pool, and we consider that created at the same time, and that's called cogenetics. So we're going to talk about the implications of cogenetic material and the ratios of potassium and argon in these cogenetic samples. So different materials absorb potassium differently, so the starting concentration of potassium will not be equal. The other thing to know is that the atmosphere contains a constant ratio of argon-40 to argon-36, and this will contaminate the sample. So because we start with different amounts of potassium, and we will be comparing this to argon-36 from the contamination, we will have differing amounts of ratios of potassium-40 to argon-36. And these ratios are going to be important in our calculations. Now, these cogenetic samples will have been made at the same time, so they will be exposed to the atmosphere for the same length of time. So that implies that the contamination amount of argon-40 and argon-36 will be the same in cogenetic material, so the ratio of argon-40 to argon-36 from the contamination will be the same in cogenetic samples. So we're going to use those ratios of potassium 40, argon 40, and argon 36 to create an isochron plot and eventually solve for time or the age of our sample. So on the left here I have my potassium 40 decay scheme, and it decays in two modes. This is a simplified scheme. One to argon 40 using electron capture, and then we have a negatron emission to calcium 40. Now we are going to need the calcium 40 decay constant, but we are not going to be really looking at calcium 40 at all in our calculations. So on top here I have our decay constant for the electron capture, which is to argon 40, and I also have the decay constant for the negatron emission, which is our potassium 40 going to calcium 40, and we're going to use those two to find this total decay constant. So now we are going to be using these constants in our formula, but we are not going to be using calcium because we are looking up for the decay of potassium into argon. So when we dig up this sample, we have to think about where this argon 40 is coming from. And that's going to be right here. We have argon 40 coming, here's our total argon 40. It's coming from two places. Let me label those. So our asterisk here is the argon 40 that is coming from the decay of our potassium 40. So we'll put a little D there. And this not sign is our argon 40 that's coming from the atmospheric contamination. So we'll put a C there. And our argon 40 that's coming right from the decay is coming from the decay of potassium 40, and it's only coming from part of the decay. So remember, our potassium 40 here is going to decay into argon 40 and calcium 40, but we only want the part of the decay that is going into argon 40, which is why we multiply it by this fraction of the decay constants. So we have the decay constant for the electron capture, which is the argon 40 over the total. So we are taking our total decay of potassium and multiplying it by the fraction that goes into the argon. So that is why this is here and why we do not use the decay constant for the negatron emission in this calculation. So now I'm going to take this and we are going to plug it in here, and then we are also going to be analyzing our sample for argon 36. Argon 40 and argon 36 comes from contamination from the atmosphere. So when I plug that in and divide everything by argon 36, this is the formula that we get, and we can see this fits a linear plot. So our y-axis will be the total argon 40 divided by argon 36, and our y-intercept right here, our by-intercept, is going to be our contamination. So that's our argon 40 from contamination divided by our argon 36, which comes from the atmospheric contamination. And then we have plus our m and our x. So our x on our isochron plot will be our potassium 40 argon 36 ratio, which means everything left here is going to be the slope. So let me write an equation for our slope. So our slope, m, is going to equal, remember this part's our x, so it goes away, it's going to be our decay constant ratio times this portion right here. Okay, so we are going to rearrange that so we can solve for time. So I've just cleaned that up a bit, and so I've just cleaned that up a bit. And so what I've done here is I've taken in the decay constants. This is our decay constant to argon right here over our total decay constant, which is right here. And I've gotten that number to simplify. And we are going to divide both sides by that number. And then we have our e to the decay, total decay constant time minus 1, so add 1 to both sides. And then I'm going to take the natural log of both sides, which will then equal our decay constant time. So I'm going to divide this whole thing by my decay constant, and that's going to equal our time, which is what we're looking for, which is going to be the age of our sample. So we're going to take that slope formula and we are going to see how to apply that to an actual graphical example. Our example comes from an article about the potassium argon isochron dating of Zaire cubic diamonds, and from their data we get this graph right here. Okay, and when we graph that, we also have this formula of the line from Excel. So we have our y-intercept, or excuse me, our y-axis right there, aligns with our y-axis. And then we also have our x-axis, which is going to go along with our x-axis down below. And then we have our y-intercept, which is the ratio of argon 40 and argon 36 that comes from the contamination of the air. So when we look at that portion on our line formula from Excel, we see we have a negative 686 number, and we can't have negative argon in our atmosphere. It turns out there was a lot of air, plus or minus, I think it was about 900 there. So our negative 686 with that amount of uncertainty can give us a positive number. And so from this formula, we also have our slope. Let's circle that. There's our slope right here. But our slope has these units on here. So we are going to take our slope and we are going to correct for units, and we get 0.18711. So now from that graph that we just looked at, the isochron plot for Zaire cubic diamonds, let's take that slope and let's turn it into a time so we can age those diamonds. So right here we have the formula of the line that came from that graph from Excel, and we corrected the slope for the units, and we get a slope of 0.18711. Just a reminder, here was our formula, and here is y equals b plus mx, where everything left is our slope. We solved and created an equation from the slope to time that's right here, and we are also going to need the total decay constant. So I've plugged in those numbers with my slope, and then we also put in the total decay constant, which is from a previous slide right here. And then we're going to solve for time, which puts our diamonds at 4.1 billion years old. Now the Earth is 4.3-ish billion years old, and so we were very close to the time that the Earth was created. And the authors have found some discrepancies in this, and that could be because we make an assumption that the potassium in the Earth's crust is at a certain level, and that the contamination is only coming from the atmosphere, but there is possibly other contaminations. Let's contrast potassium argon dating with carbon dating. Potassium and argon dating are based off the fact that potassium-40 decays into argon-40. So we are accumulating argon in a sample. So we can take the current amount of potassium and argon along with the decay rates, and we can use this to create an isochron. This isochron is used to date the sample, the time of crystallization of the sample. With a primordial half-life, carbon-40 can date samples that are older than the Earth. Carbon dating, in contrast, looks at the amount of carbon-14 that's disappearing in the sample. And it needs initial amount of carbon-14 versus the amount left to solve for time. So the initial amount is calculated based on the assumption that all living things have a constant level of C14 versus C12, and when they die, the carbon-14 continues to decay, and this constant starting level is the level that's in the atmosphere. This method dates the time of death of a sample. Carbon-14 has a much shorter half-life, and so it can only date things as old as 60,000 years.